Again, Physics 30s. In today's optional lesson, we're going to review a couple of physics principles back from Physics 20, specifically physics principles we would have used in solving both kinematics and dynamics questions. And what I want to really make you aware of is you can see this image here. This is actually a portion of the formula sheet that you're going to be provided with throughout the course, and it'll also be provided to you on the diploma exam. And you'll actually notice that the physics principles are numbered from 0 through 9. The reason they're numbered like this is because, and I'll show you how this works out in doing some examples within this lesson, is that there tends to be a lot of numerical response questions on the diploma exam where it wants you to list in the order that you apply these physics principles in order to solve a question. So it's just a numbering system that really is used to deal with doing numerical response questions. But like I said, we'll do some examples. I'll show you how it works. Now, if we do go back to Physics 20, so there's 10 physics principles on this formula on the formula sheet. There's only about I think how many of them we actually did back in Physics 20. We did this one, which we're going to review today: uniform motion, where F net equals 0; accelerated motion, where F net is not equal to 0. We definitely talked about uniform circular motion, so F net is radially inward. We talked about the work energy theorem, and we also talked about conservation of energy. And like I said, throughout the next couple of optional lectures, we'll just go and quickly review those principles are, but we're going to focus exclusively on these two today. So let's review them. First physics principle, uniform motion, where F net is equal to 0. This physics principle applies to situations where you have an object that is either at rest or it's moving at a constant velocity in a particular direction. When this situation happens, the sum of the forces acting on an object, or the net force acting on an object, is equal to 0. If the net force acting on an object is equal to 0, then it means that the forces are balanced. So a really easy example of this would just be you have a box just on a surface, and say there was like a tug of war where someone was like pulling in this direction with a force of 20 newtons, and someone was pulling in this direction with a force of 20 newtons. Well, even though you have two forces acting on the box, I mean, there's also a force from the ground and the force of gravity. We'll just worry about the horizontal forces. When you put the two of these forces together, the net force is equal to 0. So the reason being is force is a vector. So if I did want to calculate what the net force is, you add the forces together. Now, I like to use the symbol, the sigma symbol, instead of writing down F net. So instead of writing down F net equals 0, I like to write down sigma F is equal to 0, because it means you have the sum of the forces in a particular direction. So if I were to find F net in this direction here, okay, this would be equal to, well, this force points towards the left, so we'd write it down as being negative. So you'd have negative 20 newtons, plus this force points toward the right, so it would be positive 20 newtons. And that means that the net force acting on the object is 0. Or if you prefer not to use the sigma notation, you could just write down F net is equal to 0. So that's what it means for the forces to be balanced. Like, think of like as if there's like a tug of war on the object you're looking at. If you put all the forces together and they balance, it means overall at the end of the day, there is no net force. And if there is no net force on the object, well, in this case, the box wouldn't move. But you can also have a situation where you have the net force acting on an object equal to 0 and the object does move. So the best example I can give for this one, not that we talk much about air resistance, we typically ignore it in all of our calculations, but if you had a box and let's say you dropped it out of an airplane, okay, the force of gravity is going to try to pull this thing towards the ground. Now, if an object is falling and it's moving very, very fast, there is significant air resistance that's going to act on the object. And typically what happens, like the faster the object falls, the more the air resistance would be. So as this object falls, you're going to have this air resistance that gets bigger and bigger and bigger and bigger and bigger. Oh, got my little vertical line problem there. So let's just get rid of that. So it gets larger and larger and larger and larger. Okay. And then, geez, just doesn't want to cooperate with me right now. Let's try that one more time. Okay, we'll call this, I don't know, F air. You can treat it as a frictional force as well. So the idea is that air resistance will get bigger and bigger and bigger and bigger and bigger until it matches what the force of gravity is. Now, when the air resistance is equal to the force of gravity, it doesn't mean the box just mystically stops falling because the forces are balanced. It just moves at the constant velocity. There's actually a name for what that velocity is. It's called the terminal velocity of a free falling object, which is the fastest an object can ever fall. And that occurs when the air resistance is in perfect balance with what the force of gravity would be. But like I said, we don't really deal with air resistance calculations because the equation, even for the most basic model of air resistance, is quite confusing or is quite complicated. It requires a little bit of differential math, which is not really something that's going to be expected at the physics 30 level. Okay, now let's look at what kind of equations apply aside from the force ones that I showed right here. So in kinematics is just, it's the branch of physics that deals with the motion of an object, but without making any references to forces. So typically kinematics questions involve describing the motion of the object by making reference to its position, its distance traveled, its displacement, how long it's been moving for, what's its initial velocity, its final velocity, its acceleration. In terms of uniform motion, there's really only one kinematics equation you can use. Now, if I box an equation and put a number beside it, it means that equation is on the formula sheet. So on the formula sheet, we have the equation V average is equal to delta D divided by delta T. So V average is average velocity, delta D is the displacement of your object, and delta T is the time the object is in motion for, or the time that it covers that change in position or displacement. But if the object's moving at a constant velocity, we can just take that equation and just write it like this. We can just write down V is equal to D divided by T. Because if an object's always moving at the exact same velocity, it's redundant to even identify what the average velocity is. So we just drop the average subscript and we just have V is equal to D over T. So that is the only kinematics equation that can be used in dealing with the only kinematics equation that can be used in dealing with a situation where you have uniform motion. Now, dynamics, we can then talk about what the forces are, and that's what I did in my two diagrams at the very top right there. So in terms of dynamics, what equations work? Well, again, uniform motion occurs when either the object's at rest or moving at a constant velocity in a particular direction, and that happens when the forces are balanced. When the forces are balanced, it means the net force acting on the object is zero, or the way I like to write it down, this is more of an engineering notation, is that the sum of the forces acting on the object is equal to zero because all of those forces are balanced. So that's physics principle number one, uniform motion. Okay, second physics principle, accelerated motion. So this is when the net force on an object is not equal to zero. So this applies to situations where the velocity of the object is changing. And if the velocity of your object is changing, your object accelerates. That's the definition of what acceleration is. Acceleration is the rate at which your velocity is going to change. If you look at this from like a force analysis, you get accelerated motion when the forces acting on an object are not balanced or unbalanced. And if they're unbalanced, then you get a net force. So let's go back to that situation where we had the tug of war on the box. So I think, again, what I said is that we had one force pulling towards the left. We can say that's 20 newtons of force. Now, let's say the person on the right side starts pulling a little bit harder, okay? So maybe we'll say they're pulling with 50 newtons of force. Now, if I try to calculate what that net force is, so we'll say the sum of the forces in this particular direction would be equal to, so this 20 Newton force, it points towards the left, so we'll write that down as being negative. So negative 20 Newtons. And then plus this 50 Newton force points towards the right. So that's going to be positive 50 Newtons. And then what I would have here, negative 20 plus 50 would give me positive 30 Newtons. So this unbalanced force is when you kind of put the two forces at the end of the day, what's the overall force acting on the object? That's my unbalanced force. Okay. That's my net force. And what happens is if you have a net force acting on an object or a system just means you have a collection of objects, then you accelerate in that direction. So this is actually Newton's second law of motion, which states that the acceleration of an object is directly proportional to two things. It's directly proportional to one thing and inversely proportional to another. So directly proportional to that force, that's pretty obvious. Like the bigger the tug of war winner force is, the larger the net force. And the bigger that is, the greater the acceleration. Inversely proportional to mass should also make sense because if an object is heavier, then it's going to be more difficult to change its inertia and get it to move, okay? And to get it to accelerate. In terms of what the equations would look like for accelerated motion, now there are a lot of them for kinematics. So on the formula sheet, there are 5 equations that actually have these variables in it. So the variables d, vi, vf, a, and t. So d is your displacement, vi is your initial velocity, vf is your final velocity, a is your acceleration, and t is time. And these equations can only be used if an object is moving with uniform acceleration. So the easiest example of an object moving with uniform acceleration is an object in free fall with no air resistance, because in that situation, then the acceleration, if you're close to the surface of the Earth, would be equal to negative 9.81 meters per second squared. And as long as your acceleration is uniform from start to finish of your motion, you can use any of these equations, these variables. So for example, one of those equations is Vf squared is equal to Vi squared plus 2 times A times D. Again, it just depends on what information you're provided with in a problem in terms of what's the appropriate equation to use. But nonetheless, there are 5 equations that can be used for uniform acceleration. Now, as for dynamics, now we talk about the forces. Well, here's Newton's second law of motion in just a mathematical mathematical formula. So if you look at the equation here, A is directly proportional to the net force. Okay, the net force is in the numerator, so it means that the net force gets bigger, so does the acceleration. Because m is in the denominator, there's an inverse relationship between the mass and the acceleration, which means that the mass gets bigger, the acceleration is going to be smaller. I typically don't find that equation is the most useful form to apply Newton's second law of motion. What I like to do is take this equation and just quickly manipulate it for the net force. So if you do that, your net force would then be equal to mass times acceleration. Or in the engineering notation that I prefer to use, you have, I don't know if it's called engineering notation, it's just what we used when I was in engineering. We have sigma F is equal to m times A. And this is typically the starting equation you're going to deal with in solving any dynamics equation that deals with accelerated motion. Okay, let's go through a couple of examples dealing with this, and we'll try to pick examples that are going to have an application at some point later on in the course. So I think one type of problem that students typically have a bit of a tough time with in Physics 20 are problems dealing with projectile motion. The reason projectile motion is a bit complicated is because you actually have both types of motion within the same problem. You have uniform motion and you also have accelerated motion. And it's kind of up to you to identify, well, which direction is it accelerated and which direction is it going to be uniform. So let's read the question here and I'll show you how we actually can solve a projectile motion problem. All right, so you have an object that's thrown horizontally off of a 150-meter tall cliff at a speed of 10.0 meters per second. It says assume the air resistance is negligible. And I want to do the following things. I want to calculate the time the projectile is in the air. I want to determine the range of the projectile. And then I want to identify which physics principles I'm using to calculate the time in part A and the range in part B. Okay, so let's go through a solution of how I would do this. So I'll just draw a quick picture to start off with. So we have a person on top of a cliff. Okay, they're going to take an object and they're going to launch it horizontally. Now, the problem is a lot easier if the projectile is launched horizontally. If it's launched at an angle, it does add an extra complication to the question. But for physics 30, we don't need to worry about that. Okay, we just need to be able to handle horizontal projectile motions because, believe it or not, when we talk about electricity, there's going to be a specific type of problem that deals with horizontal projectile motion. Okay, if I label the different dimensions of the question here, so the cliff is 150 meters tall. Okay, we launch this thing, and then it's going to fall down on the ground. Now, I just want to point out one thing here. In terms of like the way we would describe projectile motion, this is referred to as a parabolic trajectory. I'm using this word right now because we're going to draw an immediate comparison when we talk about what the trajectory is for circular motion in the next optional lecture. Okay, parabolic trajectory. So it follows the path of like part of like what a parabola would look like. Okay, 10.0 meters per second. Now, the way we deal with the projectile motion question is that we're going to break it into two parts, okay? There's going to be motion in the y direction, and there's going to be motion in the x direction. And I'm actually going to set the question up in a bit of a chart format. So we're going to write down the x direction, and then in the x direction and y direction, we're going to identify as much information as we possibly can. Now, the first thing you want to do is you want to identify which physics principle applies to each direction, because that's going to tell you which equations you're actually allowed to use. So that is essential that you do that when you start a projectile motion question off. Okay, now, so the question is, what's going on in the x direction? Well, if you're to draw a free body diagram of what the projectile looked like, okay, so you launch this thing, and it's in the air. Now, aside from the initial point where you might need to just exert a force on the object and get it to move, from the start of the motion to the end of the motion, the only force acting on this projectile is the force of gravity. That's it. I don't see any forces acting on this thing in the x direction. If there are no forces acting on this in the x direction, then the forces by default have to be balanced. So we're going to clarify that. So we're going to say, what type of motion happens when the forces are balanced? Uniform motion. Now, if we're talking about uniform motion, there's only one equation we can actually use, and that's the equation V is equal to D divided by T. Okay, so let's see what we actually know here. Do we know the velocity of the object in the x direction? Yeah, it's 10.0 meters per second. Okay, let's establish a grid to see what's positive or negative. So we'll say positive and positive. Okay, so we're going to say, now I'm going to add a subscript here just to keep track of like what's going on in the x and y direction, because we'll have to reuse different variables in each direction. I don't want to mix them up. So we're going to say Vx is equal to positive 10.0 meters per second. Okay, do we know the displacement in the x direction? No, we don't, okay? And actually, what I'm going to do is I'm going to label what's uh, the initial where does the object's motion start and where does it end. So we're going to call this I. So that state I. So that's your initial state of motion for the object. We're going to call this state F. Okay, so what we do not know right here is we do not know what is dx. Okay, I don't know what that is. So I'll just write that down as a question mark right now. So we'll say dx is equal to a question mark. Do I know what the time in the air is? No, because obviously, because it's asking me to figure that out. So we have a problem in the x direction. So in the x direction, we have this single equation, and I know one piece of information. I do not know the other two. So you can't do anything in the x direction to start off with. So we're going to leave that alone. Okay, let's break the page up now. So I'm going to put a vertical line, and then we're going to worry about the y direction. And you have to identify, okay, well, which physics principle applies in the y direction? Because that tells me what kind of equations I can use. Well, let's go back to the free body diagram. On the free body diagram, there is a single force that is acting on your object. It points down. There's nothing to offset that force because there is no air resistance. So that's an unbalanced force. If you have an unbalanced force, it means that you are accelerating. So we have accelerated motion. Now, accelerated motion means you can use any of those equations in the formula sheet that have the variables Vf, Vi, d, a, and t in it. Okay, so let's try to identify what the variables are here. Well, this is a free-falling object. If it's a free-falling object close to the surface of the Earth, we're going to say AY, the acceleration in the y direction, and your acceleration is, well, you're moving quicker and quicker towards the Earth's surface, so your acceleration is negative 9.81 meters per second squared. That number is provided on your formula sheet in the table of constants. Okay, what else do we know here? Okay, in the y direction, we need to make use of this 150 meters. Now, here's where you have to be careful, okay? So you might be tempted to write down the displacement of the object in the y direction is equal to 150 meters. And if you wrote that down, that would be incorrect, okay? The number is right, but the problem is you haven't accounted for what the actual direction is. So let's go back to my picture. Okay, so I is just the instant where you have just released that ball. So you're no longer exerting a force on it, which is why we don't draw it in the free body diagram. F is the instant before the object hits the ground. So what does your displacement vector look like in the vertical direction? Okay, draw the vector starting at I, and then draw it going down to like whatever the height level of F is. So your displacement vector would actually be pointing down like this. So overall, what did you do in the y direction? You went down by 150 meters. And if you go down by 150 meters, this is negative, okay? Now, you'll see what will happen. If you don't put this negative in here, something weird's going to happen when you try to deal with the mathematical equation. Okay, what else do we know here? Okay, now here is a really, really, really big error, okay? So F is the instant before striking the ground. So what a lot of physics students, when they see a projectile motion question to start off with, is they look at the question and are like, okay, you throw the ball, it hits the ground, it's eventually going to stop moving. Now, I don't disagree with that. It definitely will. But the way in which we define F is F is the last instant that you are still accelerating at this rate, okay? Because we can only use these acceleration equations if our acceleration is the same number. The instant you hit the ground, who knows what the acceleration is? Like it'll be a really big number in the positive direction, y direction, to bring that thing to rest. So what you cannot say is you cannot say VF is equal to 0, okay? VF will be equal to 0 after your acceleration has changed, okay? So I'm going to make a little point right here because I'm going to call this a noob mistake, okay? So VF cannot be equal to 0, okay? Like I said, it will after you stop accelerating at that rate. Okay, so the thing with these acceleration equations is you need 3 pieces of information to get the fourth one. So we have 2, but we seem to be missing another piece of information. Now, we don't know what time is, okay? So that's a question mark, okay? I've already told you we can't say VF is equal to 0. In fact, we have no idea what VF is. So we can't use that as a variable. So the only other variable we can look at is VI, okay? So VIY. Now, look at the way in which I drew the vector that starts this motion off. It's a horizontal vector. So what's the vertical component of a horizontal vector? Nothing, okay? So we'll say because the initial velocity has no vertical component. So I think that's the tricky part, is you have to identify, it doesn't explicitly tell you this in the question, but the fact that it is horizontal projectile motion means you do not have a vertical component of your initial velocity. Okay, now we now have enough information to figure out the time, because like I said, for accelerated motion, you need 3 variables to get the fourth one. So now what we have to do is we go to the formula sheet and we find the kinematics equation, the uniform acceleration equation that has the variables A, D, T, and VI in it. If you track that equation down correctly, it is this one, is D is equal to VI times T plus 1 over 2 AT squared. Now, I'm going to add my subscripts on any of the vector quantities, so displacement in the y direction, initial velocity in the y direction, and acceleration in the y direction. Now, what good mathematical practice is in a physics question is you don't want to sub numbers in as soon as you write the equation down. We want to try to manipulate the equation for the variable we're solving for and then plug things in as a last step. Now, the one exception to that rule, though, is either a situation where you have to solve a quadratic equation or if something is 0. If something is 0, you may as well just get rid of that term because it makes the formula manipulation so much easier. So we know VIY is equal to 0. So if VIY is 0 and you multiply by t, well, this whole term's gone now, okay? So that would just leave me with dy would be equal to 1 over 2 AYT squared. Okay, we got to get t by itself, and we can definitely do that. Now, if you can perform a formula manipulation in one step, I don't need to see that work, okay? Just simply do it, show me what the equation is. I do want to see what the original equation is, though, okay? So how do we get t by itself here? Well, let's get the t squared by itself, don't worry about getting t by itself. So I'm going to multiply this side of the equation. I want to get rid of this 1/2 AY. Well, if you want to get rid of a 2 on the bottom, put a 2 on the top. If you want to get rid of an AY on the top, put an AY on the bottom, okay? Whatever you do to one side, you also have to do the other side. So we're also going to multiply this side of the equation by 2 AY. Okay, so what this does now is this is going to make the 2 on the top and the 2 on the bottom cancel, the AY on the top and the AY on the bottom cancel, and then you would be left with the equation that would be, we'll write down the t squared term first. We'll write down t squared would be equal to 2 times dy all divided by AY. And then to get t by itself, we're going to take the square root of both sides, take the square root of both sides, and then I would have my equation for t. And like I said, this is good mathematical practice. You don't want to sub numbers in right away unless you absolutely have to do that, okay? In fact, if you do courses in university, whether engineering or physics courses, they won't give you numbers. They'll just simply say, write a mathematical equation for like the time in terms of like other given variables. So you don't have numbers you can plug in. Okay, let's throw the numbers into the equation and calculate the time. So then this would be equal to 2 multiplied by, now dy is, again, from I to F, you're going down by 150 meters, okay? If you don't put that 150 there, you're going to notice something's going to be a problem, okay? AY is negative 9.81 meters per second squared. Okay, we'll calculate the time. This is part of a final answer. So if you look at the significant digits in the question, we're given two numbers. They're both the 3 significant digits. If we plug it into our calculator, what we would get here is 5.53 seconds. So that's my answer to part A, 5.53 seconds. So okay, now I'm going to fill this back in the chart. Oh, by the way, so again, if you did not write down dy as being negative, you would actually have, so here, the negative divided by the negative cancels off, which allows you to take a square root. If you don't put that negative in there, you would have 2 times 150 over negative 9.81. You can't do that. That's going to give you a non-real answer. Well, you can do it, but you can't do it in terms of getting a real number. So usually if you get a situation where like you're taking the square root of a negative number, it typically means that you just were not considering what the direction of the displacement vector is. So just something to watch out for. Okay, we know my time is 5.53 seconds. Now, this lets us deal with our problem that we started off with. In the x direction, we had too much information that was unknown. It turns out time in a projectile motion question is the one variable that links the two directions together. So now we can write down 5.53 seconds. Now, why does it link the two directions together? That's because t is a scalar quantity, okay? Time doesn't care about direction. So whether you're in the x direction or the y direction, we don't have to write down time in the x or time in the y. It's still the same thing. So usually in a projectile motion question, even if the question doesn't tell you to do it, you're most likely going to have to calculate the time the projectile is in motion for, okay? So again, just something to watch out for. Okay, now part B says calculate the range of the projectile. Now, the range of the projectile is related to this variable dx with one just extra little condition. Range is a scalar quantity. So when we calculate the range, we're just going to write down what the numerical value is, not what the direction is. So let's go to this direction and calculate it. Again, for uniform motion, there is one equation you can use, okay? So you have V is equal to d over t. Technically, you can actually use the accelerated motion equations, but you'd have to plug in a equals 0, and your initial and final velocities would be the same, but it's a lot of redundant work. So just be aware that for uniform motion, this is your one equation. All right, so we have Vx is equal to dx over t. I want to get dx by itself, so cross multiply, move the t up here, and then I would have dx would be equal to Vx times t. Okay, we'll calculate dx, then we'll take the absolute value of it. So this would be equal to, by absolute value, I mean the magnitude. So Vx is positive 10.0 meters per second, multiplied by the time, which is 5.53 seconds. So to 3 significant digits, this would give you 55.3 meters. But range is the magnitude of this, okay? So technically this would be positive towards the right. So range is just the magnitude. So we just write down without the positive sign. We would just say 55.3 meters, but we don't include the direction. Okay, so that's a review of a horizontal projectile motion. And like I said, that's a tough kinematics type question because you have to use one physics principle in one direction, and you have to use a different physics principle in the other one. Okay, let's deal with the force example. Oh, actually, we got to go back. We didn't label the physics principles. Okay, so it said identify the two physics principles used to correctly calculate the time in A and the range in B. Okay, well, let's go back and see what we did here. We got time from the y direction. Okay, so time from the y direction was accelerated motion. So we used physics principle number 1 to get the time. What did we use to calculate the range? We found the range in the x direction. And the x direction is where we had uniform motion. So again, going back to like what you could see on the diploma exam is you get, I mean, you're not going to get a question just like this because this is a physics 20 question, but what they typically say is they might say something to you like, write in the order of application the physics principles used to figure out the range of the projectile. So we have our little numerical response box, 4 little boxes here. So to get the range, what you have to do is you have to find the time first. To get the time, we have to use accelerated motion. So that's the physics principle you use first. And then to get the range, well, we did that second, and that was using the uniform motion physics principle. So we'd write down a 1 followed by a 0 on the formula sheet. That's the correct order of application of the principles to get what the range of the projectile would be. And now let's go to a dynamics question. So we have a force of 90 newtons is applied to a 40 kilogram wagon at an angle of 30 degrees above the horizontal. It tells me the coefficient of kinetic friction between the wagon and the ground is 0.070. And it wants me to calculate the magnitude of the following, or in part C, we'll identify which physics principles we're using. So I want to calculate the magnitude of the normal force acting on the wagon and the acceleration of the wagon. Now, anytime you're dealing with a dynamics question, like the immediate question that'll pop into your head is, well, what equation do I use to do this? Well, you don't have one. You can go to the formula sheet and do. What you have to do is you need to build the equation yourself. So where exactly do you build an equation from? You need to use a very specific tool that is unbelievably useful. Okay, and that tool is called a free body diagram. Okay. So let's go and show you how to draw a correct FBD. Okay. So I like to use the acronym FBD. Now, depending on how artistic you are, if you want to go ahead and you want to like draw like an actual wagon, by all means do so. I just draw everything as a box. So we'll have a box here. The box is the wagon. I really should have the FBD centered more over top of the object, but that's okay. So you know what, I'll do that quickly. Just like don't like that. Okay, FBD. Okay, now we're going to draw every single force that acts on this object. So the obvious one is, now what you usually do is you draw all forces acting from the center of the object. So we'd have the force of gravity that points straight down. I'll make this vector a little bit longer. Okay, we're going to call this FG. So FG is the force of gravity acting on the box. Now, you also have a normal force that's acting on the box or acting on the wagon. A normal force is a vector that always points towards your object and it's perpendicular to the surface. So if you were to draw your object here and draw the surface, if you were to draw a force that's perpendicular? Okay, perpendicular to the surface, that's a 90-degree angle there, and points towards your object, it would point up. Okay, so, but again, we take that vector and we always draw it from the middle of the object. So we'll just go over here and I'll draw a normal force vector that's going to point up like that. And we're going to call that Fn. Okay, now we also have a force at an angle. So it says we're pulling this thing at an angle of 30 degrees above the horizontal. So I'm going to go ahead and just draw a vector that represents this. Okay, we're going to call that, we'll deal with the 30-degree angle in a second. Now, I'm going to call that an applied force, FA. Okay, a generic push or pull on an object, we refer to that as an applied force. And we also have the force of friction. So the force of friction would be between your object and the ground. The force of friction is going to be a vector that points towards the left. The force of friction will just oppose whatever the direction of your velocity of your object is. So in this question, the wagon would be moving towards the right. The force of friction is in direct opposition to that velocity vector. So that would just be the force of friction. Now, if you had me as a teacher, I also like to draw another diagram as well. Okay, and there's a reason why I do this. Okay, it's called an MAD. What an MAD is it's an abbreviation for a mass acceleration diagram. Now, this is actually a really easy diagram to draw, but there's a very important reason I do it. Okay, so let's draw the object again. So all you have to do in the object is one, pick a variable to represent the mass of the objects. We'll label that as m, and then draw a vector that shows what direction your object accelerates in. Well, you're moving towards the right, so presumably I'm picking up speed towards the right and I'm accelerating in that same direction. So we're going to label that as A here. Now, there is one other thing I'm going to do, okay? Because we're going to do a force analysis in a second, and just like projectile motion question, we're going to break this into an x and y direction. Now, if you look at my FBE and MAD, there is one vector that is not in purely in the x direction or purely in the y direction, and that is FA. So what we need to do to deal with this mathematically in a moment is I want the vector components of this vector. Now, just be aware, technically speaking, you are not supposed to draw the components on a free body diagram. In fact, if this were a diploma exam question and it said, what's the free body diagram of this object, you would never draw the components, okay? But at the same time, the components are very useful in actually doing a mathematical calculation. So the way I kind of like compromise between the expectation on the diploma and what I think is useful is when I draw the vector components for FA, I'll do them with a dashed line, okay? So we have a dashed line that goes over here, dashed line that goes up there. And again, I like to keep my vectors relative to the x-axis. And this angle right here, I'm just going to keep it in terms of an unknown angle right now. I'm going to call it theta, okay? It is 30 degrees. We'll write it like that. Okay, the x component of the vector, we'll call it FAX. And the y component of the vector, we're going to call that FAY. Now, alternately, if you don't want to do this, you don't want to draw the vector components on the free body diagram, you can do a separate vector components diagram somewhere else on your page that shows me that picture, but you have to do this, okay? If you make use of the components, I do want to see it, okay? I'll accept the dashed lines right there, but just be aware on the diploma, don't draw the components there, okay? Well, not that you need to worry about it because right now, as of 2023, you don't have a written response part of the diploma. But if we're talking about written response on any of my tests, then it has to be one of those two choices, dashed lines or do a separate components diagram. Okay, first one, it says figure out the normal force acting on the wagon. So like I said, just like a projectile motion question, we're going to break this problem into two parts, an x direction and a y direction. Well, what direction is the normal force in? This is a lot easier to identify compared to projectile motion in terms of what direction to start off in. We'll look at the FBD. The normal force is clearly in the y direction. Okay, then we want the acceleration. The acceleration, look at the MAD, is clearly in the x direction. So this is much more clear where to start, okay? So we're going to start with the y direction. Okay, now this time around, what I want to do is I want to ask myself, are the forces balanced or not in this particular direction? So if you look at the MAD, we don't have any acceleration in the vertical direction, which means that the wagon is just moving horizontally towards the right. If it's moving horizontally towards the right, it means all forces in the y direction are balanced. Okay, now, again, if you've had me a teacher in Physics 20, this notation will make sense to you. If not, I'll have to explain it in a bit of detail. Okay, so here's why I start by writing this off. The first thing I want to do is I want to identify in the y direction, which direction do I want to be positive. So I'm going to put down a plus sign beside an arrow that points up. This means any vector that points up, I'm going to write it down as being positive. And then I'm going to find the sum of the forces in the y direction. And if the forces are balanced, which they are in the y direction, the sum of the forces is equal to 0. Now, in brackets, I'm going to clarify what is happening right here, okay? If the sum of the forces is equal to 0, it means that the forces are balanced. So this is my starting equation. Now, this equation right now does not tell you what the normal force is. So what we have to do is we have to expand it, okay? And by expanding it, we're going to create something called an equation of motion. So let's expand it. Now, here's how you do this. So what this means is, look at the FBD. If a force points up, put a plus sign in front of it. If a force points down, put a negative sign in front of it. So in the y direction. So let's look at all my different y forces. So in the y direction, and I'll just underline this. Okay, what forces do we have? We have Fn, we have Fg, and we have the y component of the applied force. Now, if those forces point up, put a plus in front of it. If they point down, negative in front of it. So the normal force points up. So we put a plus in front of it. So I'll just clarify that. We put a plus because it points up. Okay, the applied force in the y direction, that also points up. So we'll say plus Fay. The force of gravity points down. So we're going to write down a negative. And that's going to be equal to 0. Okay, now I have an equation of motion that I can solve for what the normal force is, but I'm not quite ready to do that yet because I don't know what Fay is and I don't know what Fg is, but I know information I can use to calculate it. Okay, so let's expand this. So this would be Fn plus, okay, now look at the components diagram. If you want the y component of the applied force, well, I know the magnitude of the hypotenuse of the triangle. So I know hypotenuse, I want side opposite, use the sine ratio. So to figure out what Fay is, Fay would be Fa multiplied by sine of theta. Now, I've done that expansion because I know the applied force and I know the angle. Okay, now Fg, there's an equation on the formula sheet for this. So the equation for Fg is the mass of the object times g. Okay, that's equal to 0. Now, I want to get Fn by itself. So to do that, I won't show the manipulation for this one, but you're going to add mg to both sides, subtract Fa sine theta. So I then have Fn would be equal to, and this would be mg minus Fa times sine of theta. Okay, let's plug the numbers in now. So again, like I said, good mathematical practice. We don't sub numbers in until I've manipulated the equation. Okay, so M is 40 kilograms multiplied by G. Now, some people are going to be immediately tempted to write down negative 9.81 meters per second squared. But the way in which I've written down these equations of motion is I put the pluses and the minuses in front because that let me deal with the direction. And any other number I sub in right now is going to be just magnitude of that vector. So for G, I'm just going to write down 9.81 meters per second squared. And again, you might say, well, where's the negative? Where did you account for that? Well, I did account for it. I accounted for it right here, okay? Because I identified that Fg is a force that points down. So once you put the pluses and the minuses in front, everything else is just magnitude. And that's why I like to do that as a first step. I find it confusing later in the question to start to have to sub in numbers, whether the vector is positive or negative. I just want to get that out of the way first. And again, that's a very engineering way of doing it. That's how I was taught how to do this when we built equations of motion in engineering. Okay, let's continue dealing with this. So minus Fa. Fa is 19 newtons multiplied by sine of 30 degrees. And if we calculate the normal force Fn would be equal to, you'll have to write it into two significant digits because every number in this question is two SDs. The force, the mass, the coefficient of kinetic friction. Again, we typically don't use angles for significant digits. So that would be, the number you should get is 3.5 times 10 squared newtons. And let's box that answer. I don't need you to write a complete sentence. I'll just box and be concise about communicating your solution. Okay, that's part A. Part B. Okay, I want the acceleration. Well, clearly the acceleration is in the x direction. Okay, now, in the x direction, we'll look at the mass acceleration diagram. We now have acceleration, which means that we're going to have a different starting equation here. If you have an acceleration, you have net force in that same direction. So I'm going to write down, let's say right is positive, and I'm going to say the sum of the forces in the x direction is equal to, now it's not zero this time because the forces are now unbalanced. So this would be equal to mass times acceleration in the x direction. And the reason you have acceleration is because the forces are unbalanced. Why are they unbalanced? Look at the FBD. The x component of the applied force is bigger than the force of friction. That's why you accelerate towards the right. The reason we don't accelerate towards the in the y direction is because if you take the normal force and put that together with the applied force y component, it's perfectly offset with the force of gravity. Okay, now we need to expand both sides of this equation here. So the way to do this is sigma fx means go to the free body diagram, look at the forces in the x direction this time. So what are the forces in the x direction? FF and FAX. Now, after you look at the forces in the x direction, what you do is you identify, is the force positive or negative? It's positive if it points right. It's negative if it points towards the left. So looking at the FBD, FAX is a force that points towards the right. So we'll write that down as being positive. Okay, points towards the right. FF is a force that points towards the left. So we'll write that down as being negative. So we have FAX minus FF is equal, not equal to zero, okay? My goodness, it's not equal to zero, okay? Now, here's another reason I do the mass acceleration diagram, aside from it's just helpful to know what direction you're accelerating it is. Acceleration is also a vector. So you also have to pay attention to what direction it points. If you look at the MAD, the acceleration points towards the right, so we'll just write it as being positive A. If the acceleration pointing towards the left, then we'd write it down as being negative. So I really like to do the MAD because it reminds me you have to pay attention to what direction you accelerate as well. Okay, and again, this was negative because it points towards the left, and this is positive because it points towards the right. Now, we can't quite calculate acceleration yet because you don't know exactly what FAX is, and I don't know what the force of friction is, okay? But just like with the y component calculation, if you know the magnitude of the hypotenuse, which is 90 newtons, and you want side adjacent, well, this time you use the cosine ratio. So it would be FAX becomes FA times cosine of theta, subtract. Now, just like with FG, there's also an equation for what FF is. So the equation for FG is m times g. The equation for the force of friction, specifically the kinetic friction, the force is constant no matter, like roughly constant no matter what your speed you're moving at. That equation is equal to mu, which is the coefficient of kinetic friction, multiplied by the normal force. Now, I'll add one subscript here because there is static friction. So static friction is if your object's, you're trying to make an object move, but static friction prevents motion. Kinetic friction is there's friction on a moving object. We're going to add a subscript K here just to clarify it is kinetic friction. So FA cos theta minus FF is mu K times Fn, and then that is equal to M times A. Okay, to get A by itself, all I have to do is divide both sides of the equation by M. And again, I'm not subbing in any numbers until I have that variable isolated. So we have FA cos theta minus mu K Fn divided by M. Then we can plug stuff in, okay? Okay, FA, we know it's 90 newtons. Multiplied by cosine of 30 degrees minus the coefficient of kinetic friction. So that would be 0.070 newtons. Now, as for Fn, do you use this rounded number for part A or you use the unrounded answer? Either would be acceptable if this is a written response question. Sometimes, though, you might have a multiple choice question as A and a numerical response for B, in which case it'll tell you. It'll say, like, use your rounded response from this to use the next part. So I'll just use the rounded answer just because that's what I have here. 3.5 times 10 squared newtons. Again, just note right here, I'm always including my units beside all the numbers. That is an expectation. Okay, divide by M, which is 40 kilograms. Now, before you plug this into your calculator, just one thing about the order of operations. Just make sure that you have everything in the numerator in its own set of brackets because you have multiple terms in the numerator. Otherwise, you're going to get a calculation error. Well, not a calculation error. It'll just do the order of operations incorrectly. Okay, calculate the acceleration, and you should get a number to two significant digits. That would be 1.3 meters per second squared. Okay, let's box that answer. That's your acceleration. So, like I said, this if you didn't have me as a teacher of Physics 20, this approach will be like quite a bit different compared to how one of your previous teachers did it. Again, this is a very much in line with like how I was taught how to do this when I was in engineering, and like I really like this just because it deals with getting rid of the positive and negative signs initially, so you don't have to worry about it for the rest of the question. I mean, if it did say what is the normal force direction, what's the acceleration direction, go back to your FBD and MAD and just add it in there. Okay, now we do need to also identify what the physics principles used were to calculate this. Well, this is really simple to see. Okay, how do we get the normal force in part A? Well, the normal force in part A came from this equation. Sigma Fy is equal to 0, okay, which is the same thing as F net is equal to 0. Sigma F net, same thing. So your normal force came from physics principle 0. Okay, how did you get the acceleration in B? Oh, it's so obvious. Like the principle is called, you're asked to calculate acceleration, and the principle is called accelerated motion. But look at this equation here. Okay, if you want to write it down in the net notation, it'd be F net, okay, is equal to mass times acceleration. And because it's actually equal to something that is not equal to 0. So if we go back here, that's physics principle number 1. F net is not equal to 0, so we'd label that as 1. So once again, if this were a numerical response question where it just said, calculate the acceleration of the object and list the order of the physics principles required to do this, well, you have to find the normal force first, because if you don't have the normal force, you can't find the force of friction in the x direction. And then once you have the normal force from the y direction, so the normal force came from F net equals 0 in the y, then you go to the x direction where you have accelerated motion where F net is not equal to 0. So the order of the physics principles this time would be 0 followed by a 1. And like I said, that is a question you're going to be asked a lot on the diploma. Okay, it'll ask you to do a calculation, and then it'll say, well, what order did you use these numbered physics principles to do it? Okay, so that's a review of those two principles, uniform motion and accelerated motion. And then the next optional lecture, we will talk about circular motion, and I will speak to you then.